welcome to the module on the Vander waals equation. We came to know that the real gases deviate from ideal behavior. Therefore, ideal gas equation has to be modified, then only it will be applicable to the real gases. This modified equation is known as the Vander waals equation. We all know that real gases show deviation from the ideal gas or ideal gas law because molecules interact with each other. Now we have to think about the condition in which the real gases show ideal behavior. Let us observe the graph once again, and you have to find out the condition in which real gases obey ideal behavior. You can see that all the gases show ideal behavior at low pressure and high temperature. So we have to think what happens to the behavior of the gases at high pressure. I will explain. Please listen. At high pressure, what happens to the molecules? Let us observe the movement of gas molecules on applying the pressure. The molecules of gases are very close to each other when we apply the pressure. Now, molecular interaction starts operating. Due to these molecular interactions, molecules do not strike the walls of the container with full impact because these molecules are dragged back by their other molecules due to their molecular attractive force. So we can say that the pressure exerted by the gas is lower than the pressure exerted by the ideal gas. So we have to modify the ideal gas equation. A correction factor is to be added to the pressure term of ideal gas equation, and the new pressure term is P ideal is equal to P real plus A n square by V square. Here you can see a constant A which is known as Vander waals constant. We understood that at high pressure there arises an attractive force between the molecules. At high pressure, repulsive force also becomes significant. We know that repulsive interactions are short range interactions and are significant when the molecules are almost in contact. The repulsive forces causes the molecules to behave as small but impenetrable spheres. The volume occupied by the molecules also becomes significant because instead of moving in the volume V, they are now restricted to move a volume of V minus NB, where NB is approximately the total volume occupied by the molecules themselves. Here we can say that B is a constant. So we modified the pressure term and volume term of ideal gas equation. Having taken into account of these corrections for pressure and volume, we can rewrite the equation as P plus A n square by V square into V minus NB is equal to nRT. This equation is known as Vander waals equation for n moles of the gas. In this equation, n is the number of moles of the gas. Constants A and B are called Vander waals constants, and their value depends upon the characteristics of the gas. The value of A is the measure of magnitude of intermolecular attractive force within the gas and is independent of the temperature and pressure. If the value of n equal to 1, we can modify the Vander waals equation P plus A by V square into V minus B is equal to RT. This is the equation for 1 mole of a gas. So we discussed about the modified equation known as Vander waals equation. Now we can discuss about the measurement of deviation from ideal behavior. The deviation can be measured in terms of the compressibility factor. Compressibility factor Z, which is the ratio of product of pressure and volume and nRT. Mathematically, we can write it as Z equal to PV divided by nRT. We know that for an ideal gas, PV is equal to nRT. Therefore, can you calculate the value of Z for the ideal gas? Yes, Z equal to 1 at all temperature and pressure. I will show a graph which is a plot of compressibility factor Z versus P. What is the peculiarity of lines for the ideal gas in the graph? Yes, it is a straight line parallel to the pressure axis. And for gases that deviate from ideality, the value of Z deviate from unity. Can you identify the condition at which all the gases behave ideally from the graph? Yes, you can see that at low pressure, that means at very low pressure, all the gases have shown a value of Z equal to 1 and behaves as ideal gas. So, a gas behaves ideally when the value of Z becomes equal to 1 and it takes place at very low pressure. Now, we can think about the behavior of gas at high pressure. Here, all the gases have Z greater than 1. So, what we can conclude? Yes, at this condition, gases are more difficult to compress. At intermediate pressure, most of the gases have Z less than 1. Thus, gases show ideal behavior when the volume occupied is large, so that the volume of the molecules can be neglected in comparison to the volume of the gas. Hope you all understood about the Vander waals equation. Thank you, dear students. Thank you. We will meet in the next class.